Okay, I guess everybody is here, so please welcome disconnected. We'll be talking about Python internals.
Okay, so hey, I'm disconnected. You probably already know me, and I'm going to talk about Python internals, or how does Python work. And this presentation is long. It has actually two parts. So the first part is I would tell slightly less technical. And the second part, in the second part, we will go through the CPython C code of a specific example of code. And we'll try to see what happens under the hood. So let's start. So from you probably know that I work on security and I have a blog on the internet. But coming back to Python, so we all use Python, right? But the thing is that probably all of us actually use CPython, which is one of the implementations. And if we look over like hello world in Python, you could write it like this, because obviously duck typing, right? You can add two strings, because why not? And yeah, so coming back to CPython. So CPython is actually a reference implementation of Python language. That means that there are other implementations which we'll discuss in a second, but basically this is the thing that you download when you go to like python.org or when you go to the Microsoft Store and install Python from there, because apparently now you can do that. And the thing is that it's open source and it's on GitHub, so you are free to look through the source code of it, or change it, or improve it. The thing with Python is that there is no standard in Python. Like with C or C++, where in C++, for example, you have C++ 11 or 17 or 20, and yeah. But there are PEPs, and PEPs are actually like Python enhancement proposals. And my question is, who was at that site ever? Like dev PEPs? Raise your hand. Wow, quite a lot of people. So I was actually asking about this particular URL because there is like the index of PEPs. Here's another example of a PEP, which you probably know. But basically, they have some category of PEPs, and personally, I didn't know about that. So I learned about that when I was doing this talk. So I found it interesting. So you can see that, for example, they have a particular PEP that describes bug fix releases for CPython, which might be interesting, or style guide for C code, or Python code, which is Pwndbg, right? And as I said, there are different Python implementations. So, for example, you have PyPy, which is a different implementation. It's actually a faster Python, at least usually. And the reason is that it uses a JIT compiler. So it takes the code and tries to compile it into a native code. At least the parts that are often used so that it can execute faster. Then you have Python, which is Python on JVM, which means that you can use it with Java and other languages that are on JVM. Then there's IronPython, which is the same but on .NET. And the reason for those two is that you might have software written in Java or C#, and you might want to write plugins for it in Python or additional code. So why not having those Python implementations there and plug it in? Then you also, and this means that basically from Python or IronPython you can use all the classes that JVM or .NET provides you. So it's like Python language with all the Python libraries, or not usually all, but most of them, but also with the libraries from those frameworks, which is nice. Then you have MicroPython, which is Python for microcontrollers, which is not that big thing, I would say, but it's there. And then there's Cython also, which is Python and Cython compiler. And actually Cython is like an extended Python language, which lets you to introduce some kind of variables that will be statically typed, which will have fixed size, like integer of 32 bits, instead of integer which will make itself bigger whenever you need it. And because of that, if you use Cython, the code with the static types, the code will be faster. but we are not going to discuss this today. But just for you to remember, Cython is a different thing from CPython. Because CPython is the reference implementation written in C, and Cython is this Python and Cython compiler. But let's go back to CPython. So the thing with CPython that probably most or all of you know is that CPython is slow. And we will see some reasons for it during this talk. But one of the reasons is the duck typing that is there. And we'll see how things works under the hood when you do some operation, like how many checks are there for different things. But the thing is, should we care about this, that it's slow? We choose Python at the first level for a reason. Maybe because we liked it. Maybe because the programmer time is expensive and writing in Python is fast, or prototyping in Python. Or maybe because we want to hack some tools or some features into our applications. And the question is it always true that CPython is slow? That might not be the case if you are using, for example, modules written in C like NumPy or SciPy. Because if you use the types from NumPy, the types are the low-level ones in C. So for example, you might have a NumPy array of integers 32 bits, and this will not have all this bullshit or overhead from CPython integers. Obviously, if you will grab these values from the NumPy array into CPython, retrieve some value, this will box it into a Python integer. So this kind of thing will be a bit slow. But if you do work on NumPy arrays, you probably also use all those other operations on the arrays itself. And another thing with CPython is that it has global interpreter lock. And this talk is not about GIL, but it's there. And the thing with it, what GIL actually means is that at any given time of executing Python code, only one thread can execute Python code. That's not 100% true, but the thing is that GIL is sometimes released, for example, when some C operations are done or when I/O is done. So you might actually launch threads in Python, but those threads might not be that efficient because of the GIL. But it might be that if the program actually will be efficient enough, depending on what you actually do. But yeah, it's still a problem. And you can also have some modules written in C that would either use threads or would release GIL as well, like NumPy. Okay, so I'm going to talk about internals a bit now. And by the way, if any one of you have any questions at any given time, you might raise your hand and we might answer this question right away, because there will be a lot of stuff through this talk. So if you don't understand anything, just ask, because why not? So the thing is that under the hood, everything, or maybe not, because I'm not 100% sure, and this statement is, such statements are probably never true. But under the hood, everything is a Py object, or actually a pointer to Py object. A pointer is like a reference, but in C. And so in C, you have this Py object structure, which looks like this. So basically, we have this structure here, and first of all, it has this underscore Py object head extra, and this is a macro. Macro in C is something that will, the compiler will actually, or actually preprocessor will actually replace this thing with something else during the compilation or parsing. Yeah, and this usually is an empty macro, so I'm not going to cover it. It's used sometimes whenever you are compiling CPython for debugging purposes. So it might be that all the objects will have some additional fields just for debugging stuff. So that's not really interesting. The next thing is the field OB ref count, and this has a size key type. This means like sign size. And this is a reference counter. It's for memory management. And later on, we have this pointer which is called ob type, and this is a pointer to a type object. So there are type objects there, and each type object, so each variable you create in Python actually has a pointer to its type. You can think of it as the attribute dunder class, or the magic attribute dunder class dunder in Python of a given object. Okay, but the question is, where is the object's data stored in? Because I told you that this is a Py object and everything is a Py object. So where's the data? Like if I create a Python integer, it is a Py object. So where is the data here? Because we are only having a pointer to a type object. Any ideas?
Immediately after.
Louder, please.
Immediately after you cast it.
Immediately after. Yes, because so the thing is that let's look over an example of a type or actually like object type in Python. So for example, integers are actually structures of this underscore long object. And the thing is that it has two fields. So first of which is PyObject varhead. And the thing is that PyObject varhead is a macro that says, okay, I want to have here a field called OBBase, which will be PyVar object. And this PyVar object actually has two fields. Again, OBBase, which is PyObject, and OBSize, which is like size of variable data there. So that's the first field of the long object. And the thing is, why is it made like this? Because there is no inheritance in C. Like you can inherit from PyObject, so you need to contain it as a first field, for example. So that's like the pattern there. Like all those objects start with this PyObject varhead under the hood. And yeah, it contains the OBBase and OBSize fields. And then there is this data field, which is called OBDigit. And this is an array of one element. And this is not necessarily true, because that's another ugly hack in C, which we'll see in a second. So yeah, that's the question. Why isn't just one element there, or even an array at the first time? So to search for the reason, let's look on how long objects are created. So this is pylong_new. This is a function which is called whenever you're creating a long object in Python or integer, because in Python 3 this is the same thing. And so in this function, the interesting part is here, because here we allocate memory, and we actually allocate size multiplied by the size of digit elements after the OBDigit field, because we are actually like taking offset of the OBDigit, which means we want to allocate the number of bytes up to the OBDigit field, which was here, and then we want to allocate the memory for the OBDigit field. So this is an array. It's supposed to have one element, but we are actually allocating more. So this is an ugly hack in C, because C doesn't have bounds check whenever you are accessing array elements. So you will be able to actually like access, for example, element of index 5, even though you might have 3 elements. So they are kind of exploiting this behavior in C to have objects that might have like bigger sizes than they would have usually. They could actually have some kind of pointer here for the data and just allocate this data again, but then they would need to make 2 allocations, which is like kind of pointless, because those 2 objects would then exist in different places in memory, and that would be a bit slower in some cases. Okay, as I said, memory is managed by reference counting in CPython. And we have this OB_refCount field. And so there are some functions or macros that are being used for increasing or decreasing the reference counting. What's that for? That's for, so whenever the ref count goes to 0, or maybe -1, I'm not sure, the object dies. And the CPython knows that it can deallocate the memory for this object. Okay, so here's this PyIncref function, and it actually increases this value of ref count. And the thing is that they actually use macro PyIncref because the function starts with underscore. So the question is, why do they actually use a macro instead of just calling this function? The reason is that they actually cast whatever is coming to this macro, like this OP argument, to PyObject. Because you might use this PyIncref with a different type, and you don't want the C compiler to warn you that you have mismatched types whenever you are calling this function. So they just made a macro to make the cast. Okay, and another thing about CPython is that it's a stack-based virtual machine. And what does it mean? That means that whenever you have operations that are being made, both the arguments and the return values of those operations are stored on a stack. So CPython internally keeps a stack, like a data structure, and when it executes stuff, it puts the values onto this stack and or pops the values of the operations. Okay, and let's look for an example of CPython VM. So an example implementation can look like this. So one disclaimer here. That's not the full picture, because the thing is that the CPython VM actually executes like code objects. So for example, a module is a code object, which we'll see a bit later. A function is also a code object. And so whenever you're calling a function, there is a function inside of the CPython interpreter called something eval, or something like that, and it contains a loop that looks similar to this. So this loop here actually first gets an opcode, which is like an code of the operation that is supposed to be executed, and then it switches or dispatches the logic based on this opcode. And there are many different opcodes for given CPython version, because the opcodes might differ between versions. So for example, there is load global, load const, or function, which we'll also see later on. And this is how it looks in the code. If you can see, we are on 1061 line in a file called ceval.c. The links on the bottom, so probably not everyone sees that. The thing is that they use some kind of macro again, which is called target. And for example, they have target knob. Knob is actually no operation. So there is an instruction which basically tells the interpreter, do nothing. Because you might sleep or wait for something. I mean, sleep in a kind of weird fashion by executing some instruction. And this target macro is actually doing case for the switch, but also doing some kind of like magical thing which is there to optimize interpreter even more. But that's for computed gotos feature in C. And if you are interested in that, just Google that, because there's a very good article about that, like computed gotos. Anyway. So that was an example of CPython VM, and there are, for each of the instructions that are there, there's this target with like some logic, which we'll also analyze later. So let's look at a bit simplified flow of invocation to execution of a given Python script. So what happens when you are doing Python script py? And this will be on a like high level, because the thing is that whenever you're executing Python script py, the Python interpreter or the binary or the process starts, it actually parses the arguments, then it initializes itself. Like there's a lot of logic that happens there. But the interesting parts are that, for example, the first thing that happens, well, necessarily true, but one of the things that happens is file decoding. So that's the thing that you had to specify in Python 2 as coding UTF-8. And in Python 3, the UTF-8 is default encoding, but in Python 2, you could actually have non-text encodings like hex or ROT13. Why would you need that? I don't know, but they removed it. The next thing is tokenization. So basically, it converts the code into tokens. You can actually look how it works by using the tokenized library like that from your command line. And that's been done on the code that you have seen before. So for example, we have like a token called encoding, which then contains the string. I mean, the string is the next token. Or actually the value of the encoding, I'm not sure. But basically, this gives you those tokens. And then those tokens are then parsed then parsed for other things, like AST creation. So AST is abstract syntax tree, and for example, there is an AST built-in library which you can use to parse some code. Then you can dump the AST tree, like the abstract syntax tree, and for a simple assert 1 equals 2, this looks like this. So we have this assert node that contains a test field which has a compare node assigned. On the left side, it has a number node which has a value of 1. And then it has operators, which is equal, and comparators, which is none with value of 2. And then it also has a message field, because you might have messages on assets. And later on, there's compilation that's happening. And this is a bit complex stuff, but there are two things that are happening, more or less. One of which is peephole optimizer. So the peephole optimizer is actually an optimizer that optimizes very simple things, because you don't want to spend a lot of time on optimizing things whenever you are launching Python code scripts. So, for example, it optimizes things like 2 plus 2 and changes this like constant expression into 4. But if you would multiply 2 with a very big number, it would probably not optimize it, because that optimization would take too much time, or it's too complex, or something like that. They don't really want to do a lot of optimizations there. They don't want to spend time on that. And then there is the compilation to Bytecode. So the Bytecode contains those opcodes and arguments for them, and which we will see also later on. And this creates something that the CPython virtual machine understands. And later on, you have the execution in the virtual machine. And as I said, this is probably oversimplified. So don't take this for granted, but that's more or less what happens there on a high level. Next thing I want to discuss is bits files, PYC. So those are those files that are created in, for example, the package directory whenever you are importing a module. And this contains 4, maybe 5 items, more or less, depends on the Python version. And we have an example of such a file here. So if we would have a file a.py, which contains just x equals 1, we then import it, and then we display its content in a hexadecimal dump, so that if someone is not so familiar with that, we have the bytes here written in hex notation, and then here are those bytes written in ASCII. But when a byte is not printable, then it's a dot here. Because, for example, you cannot print 0 byte. I mean, there's no like character for 0, so that's not really printable byte. And the thing is that this PYC files contains of magic number, which is like a kind of magic value that tells you this file is a PYC file for Python 3.6, as in this example. So for Python of a different version, this magic number will be a bit different. And this you can actually use it to recognize such files, but that's not necessarily true. I mean, you can create any file with any of those values at the start, so this might not always be true, but usually is. Then you have a timestamp, well, written in bytes, so you cannot really read it. It's 4 bytes as well. And then you have the size of the code, I believe. So this is 4, because that's written in little endian, which I'm not going to cover now, but basically you have an integer of 32 bits, you write it a bit from the other way. I mean, it's bytes. And then you have all the module code object. So we can actually create such a PYC file, and we can parse it manually, and then do something with it. So the thing is that this module code object can be loaded via Marshall loads of those bytes, and you can then execute it via eval. So let's try this. I have a file like this, a.py. By the way, does everyone see that? Raise your hand if you can see this. Okay, I can see hands at the end. That's good. And then I have this marshalling code in marsh.py, which looks like this. So we import the struct, time, and marshal modules. Then we open this file from PyCache. We read it in the binary mode. That's important. Then we unpack the first, sorry, not the first, but the second 4 bytes, the data 4 to 8, as integer 32 bits. That's how struct works. I mean, the unpacking of values. We convert it to ctime so that we can see the time that's stored there. And we also do the Marshall loads of the bytes from the index 12 up to the end. And we evaluate it. Yeah, so let me run it. Okay, so the first thing is that the date here is the date of the last modification of this file, of this a.py file. And I modified it today, so at this time, which is not necessarily true, but that's my time on the VM for some reason. And then there's the C, which was the return value of the evaluation of these Marshall loads, which was not necessarily the thing I wanted to do, so let me do it a bit differently. I didn't want to evaluate because it just executed this module, which doesn't really have nothing interesting. Like, we had this full function, so we can probably execute it because it was eval. And as you can see, we evaluated it. But we loaded this Marshall loads, and let's see what's that. That's actually a code object. Maybe I'll do it like this, so that we will be able to see the things on the other side. Okay, so this code object actually contains a lot of cool fields that start with CO. And in IPython, we can actually list that by doing this kind of magic thing with star and question mark. So let's see what's there. There we have like this many fields, starting with CO, like arg count, cell vars, code, consts, file name, or flags, or CO names, var names. So let's inspect some of those. So for example, the file name is just this path to the file path. The consts then is like foo, 1, 2, 3, 4, and no, and also a code object. The thing with code object is that we had a function defined in this module, which was foo. So as I said earlier, the foo is another code object. And the module itself, which is also a code object, it stores the code object of the functions that are defined there as constants. Like there's this CO const. What else? Maybe like some names. I'm not sure if I showed it. Okay, so here are the names that are defined in this module, like identifiers. This is the sum global and foo. and so on. So this code object contains like all metadata about this code object. And the good thing is that it's exposed to us, so we can do stuff with it, which I'm not going to cover today, but it's nice because you can like inspect it in runtime. And those fields are used by the VM or CPython VM under the hood, which we'll see later. Okay, so we had this PYC file, and the thing is that when we have a module, either a one that is PYC, or actually, sorry, if we have a Py object, which is a function or a module or a class, we can disassemble it. And we can also disassemble code objects. So let's try this. And there's a built-in module called this for that. Which obviously have a function called this as well. So for example, the code, the bytecode for this module was now disassembled into some kind of like readable representation of what happens here. So for example, here we have this load const opcode that loads the code object foo. Then it does load const of foo again, I mean the foo as a string, and it makes the function. So those three things happens each time you import the module, actually for the first time whenever you're executing something. So the function is there, but it still needs to be like created by the interpreter, which kind of sucks, right? Because you have written the function before. But this is because you might modify this function at runtime. Since you can modify it at runtime, you can. That's why like creation of function needs to be done at runtime as well. But anyway, let me also see you the CO code field. So this CO code field is a byte array, or byte string actually, which contains the bytecode for this module. And that's not particularly interesting here, but that's good to know. And now we'll come to the C part. So here's an example of disassembling some foo function. And we'll go through all that C code that's happening, maybe not all, but a lot of C code that's happening whenever those things are executed. So coming back to this module, it actually has like 4 or maybe 5 columns. First of which is line. The second one is here, which I will describe in a second, but I wrote ADR for address, which is here. So this is like the address of a given opcode. Then you have the opcode itself, and then you have arguments, which might be, the display here might be enhanced, like showing you what exactly is being fetched by this index. Because this index here, for example, for maybe load const, is the index of this constant value in this code object in the co_consts field. So if you have the co-consts, the order of the items there really matters because they are used here in the bytecode. So let's start with the first one, which is load fast. And we have the argument x here. So probably this might be like a function argument called x. And let's see how this looks like in the C code. So in this C eval loop, we have this target load fast. And then, as I said, there's this target macro that might be defined differently. So for example, if you are not using this compute go to feature, then this target macro just does the case for the switch for opcodes. Okay, and then we are actually getting the local, because the load fast loads like local values. And so there is the getLocal macro that, as you can see, is defined to, for a given index, just retrieve the given index from like an array called fastLocals, which is there. I don't really know why they don't use fastLocals, or there is an idea for that. Like, why are they using the macro here instead of this? Anyone? Because they could just remove the macro and use the thing on the right side. But the thing is that they might want to trace this thing, like getting locals, for debugging purposes, for like finding bugs in CPython whenever they implement something new. So they probably have different definitions of this macro based on some compilation flags. And probably that's the reason why they use macro-view. And then after we fetch this value from the CO, probably and locals or maybe names or something different, maybe not really CO counts because CO counts is a different thing. But one of those fields from code object. By the way, someone just asked if I contribute to CPython. Yes and no, because I had maybe like 2 pull requests, which were really small, so I wouldn't call it contributing a lot or something. Anyway, after we fetch this value, we check if it's null. And null in C is a macro for value of 0, because this is a pointer, and if the pointer is 0, that means that like it doesn't exist or something like that. And in this case, Python will actually throw an exception called unbound local error. And the reason for that is that you might have a function that tries to reference something that in theory from the code is supposed to be a local variable, but it's not there in the locals because it was not defined or something like that. And you will get this error. Probably we can simulate this behavior like this. Whoa, sorry, I clicked something. Yeah, so we created a function that references this. Okay. How the hell I did that? Because it locked my screen on the left side, or maybe, oh okay, I didn't have, never mind. I know what happened. It changed from mirror to like extended desktop, because I clicked something on the tab bar. Marks are terrible. Anyway, please come back. Okay. Okay, that works now. But basically, coming back, I have defined a function f that tries to add 1 to s, and s doesn't exist there. And when I call the f, I got unbound local error. So this is the case. The local variable was not there, and so we retrieved like a null in C, and we got this error. Yeah. Then, in this load fast, we have incrementation of the reference count, so that's the thing we have already looked at. And then we have push of value. So this value that was retrieved from locals is then pushed into the stack, into the internal stack of the CPython VM. And regarding the stack, there are a lot of stack manipulation macros. Oh, someone asked why there is no break in VM's loop switch construction. Because they use gotos. I mean, well, first of all, there is fast dispatch. How do you know that it doesn't do break? It could, but they use gotos anyway. Because that's basically the same thing, but just with a slightly different semantics. Anyway, coming back to stack manipulation macros, we have a lot of them, and in the end, the push macro does a basic part push. I didn't show you the transition from it, but trust me, it does the basic push, which takes a stack pointer that's there, it points to the end of the stack. So there's this stack data structure, which is continuous memory, and there's this stack pointer which points to this memory. And so we put this value on the element of this, where the stack pointer points, and then we increment the stack pointer. So we make it that it points to the next element. So yeah, that's here again, and let's assume that the thing on the right side is our stack. So, and the SP is stack pointer. So previously the stack pointer pointed to the top, and now it points one element further, and we push the X item, which was the argument for the load fast, to the stack. So we don't really know what the X is, because that's just a disassembly, that's not really like showing the full picture here. So there's this X on the stack now. And then we have this fast dispatch. So this fast, there are two macros, and again, this is a macro and not just go to fast next opcode, because you might have different macro definition for like debugging purposes, for example. Okay, does the stack go towards higher or lower addresses? Well, since you increment the stack pointer, then it means it grows towards higher addresses. Or actually, that's not true, because it depends on the architecture you're running at, because you might have architecture where, well, maybe not. That's a good question. Anyway, probably, I mean, towards higher addresses. Let's assume that, because that's what's happening on most of the computers at least. If my assumption about architecture is true. Anyway, coming back to the fast dispatch, we are just doing go to fast next opcode, and this go to fast next opcode, I mean, there's a label for that in C, right? In this big pile of code. And so it does a lot of stuff. First of all, it said the F here is like a frame object. And it says that, oh, last instruction is the current instruction offset. We are not going to like go deeper into it. And then you have this if PyDtrace line enabled, maybe dtrace line. So the thing is that you can compile CPython with some feature called dtrace. Maybe it's debugging trace, or maybe it's like the dtrace software. I have no idea, because I haven't used that. But there's this if condition. The question is, does it execute always, even if we don't really use this feature? It doesn't have to, because if this PyDtrace line enabled is a constant that evaluates to false, then the compiler will remove this thing. And so we want to do this check, because that check is probably redundant in most of the cases. So the code is there, but it doesn't necessarily go into the binary or the program Python that we are running, and it might not get executed. Then we have this huge if statement, or actually if block, which is there for line-by-line tracing support. So you might have this _py _tracing possible thing, and then in tstate, which is probably thread state, I'm not sure, there might be a trace function pointer, like a pointer to a function that you are using for tracing. And if it's there, then you are somehow executing it. We won't really cover it, because that's probably also for debugging. Maybe that's what Pwndbg uses. I have no idea again. And in the end, we have extraction of opcode and argument, and it's again done by a macro. We'll see a lot of macros here. And oh, by the way, this macro starts with do and ends with while 0, and it contains a block like this. So this is some kind of like C hack for creating multi-line macros, so that those macros can be used in if statements whenever the if statement doesn't have the brackets, so that the next else won't be able to execute, for example, the next instruction that would be here if we wouldn't use the do while. That's a bit complex. If someone codes a lot of in C, then probably they know about it, but that's not important that much. So basically what we get here is we get the next instruction, we call it a word, and we retrieve opcode and arguments for this word. And this looks like that. So there are again macros for that, and those macros differs whether we are using big endian processor architecture or little endian. And that's related to how values are stored inside of the memory, whether you are storing like 32-bit integer from the left to right or from the right to left. But the logic here is not important. But that's good to know that there is such a thing like endianness. Whenever you are dealing with some protocols, it might be handy. So now, after all this code for fastnext opcode, when before we was at this load fast that jumped into fastnext opcode, we now execute next opcode. So just to recap, that's what I said. We was in this load fast, and we executed this bunch of code here, and the thing that we have seen before was this fast dispatch that jumped to this fast next opcode thing. And so the next opcode is load const. So it will just load the const value, which is 0 here. The argument is 1 because it's the index in the code object called const fields. And the logic is pretty simple. The logic looks like that there is a getItem macro being used, and this getItem macro is actually for getting items out of tuple from a given index. Okay, they use it here. Because the co-const field is actually a tuple, so that makes sense. Then they increment the value, and then they push the value onto the stack. So it was pushed, so it's here on the next element. And also, since it was pushed, the stack pointer moves a bit to the next element, of course. Then there's fast dispatch again, so we will move into next opcode, which is compare operation. And the compare operation, you put here an argument of 5, which is not an index in an array, because that's a value that's being mapped to a given comparison, which we'll see a bit later. But basically the comparison here is this greater or equal to that. And so we are in this compare op, and the first thing we do is since comparison takes 2 arguments, because something's on the left side and something's on the right side of the comparison, we just retrieve those 2 elements from the stack. So here we execute the pop operation. So coming back to stack manipulation macros, the pop, here again a shortcut, the pop actually executes basic pop under the hood, or a logic that's similar to it. And this retrieves the value at the stack pointer and then decrements the stack pointer. So the right will actually be 0, and the stack pointer will move upper. I mean, the lower addresses in this case. Okay, and then we have the next instruction, which executes top. So coming back to stack manipulation macros, the top is a macro that just takes the previous element. It doesn't decrement the stack pointer. That's kind of important because the element is still there on the stack. Because one disclaimer, the way the stack works is that we kind of assume that whatever is after the stack pointer is like trash data that we won't really use anymore. So this 0 here is probably won't be used anymore by the code here. But it's there because it was there and no one cleared it, because there is no purpose to clear it at this point. So yeah, we retrieve the item, which is the left, and it will be the x value, which is an unknown object, right? Because we don't know what to get passed into this function. Then we have the CMP outcome function, which will jump in, and there will be a lot of code. Probably the most of this presentation. Because the thing that whenever you are comparing 2 values, where one of them is a constant, it doesn't have to be constant. But whenever you are comparing 2 values, there is tons of code that needs to happen just because of tag typing. Because you need to be sure that you are launching the proper comparison operation for given 2 types. So let's dive into it. So just to sum up, the arguments here are the op r is like this greater or equal than, the left is x, and the right is 0. And let's put it on the bottom side, this CMP outcome like call. So here is the CMP outcome function. It contains 2 columns, by the way. Yeah. And so it starts with defining the result. because the result needs to be like, I mean, they have some kind of result, we're able to track what's the result of this function. It doesn't really mean that the result is being returned, because they returned a phi object, I mean pointer to a phi object, which they assign here actually, like either pi true or pi false. But sometimes they also return something different, which you'll see in a second. Okay, and then there is a switch for a given operation. And then we have different cases. Like PyCMP is not in, exception match, which is another pile of code actually, which couldn't fit into the first slide. So coming back to it, whenever you are doing the is comparison, like, let me show you. So whenever we are doing the something is something comparison, the compare op will get this is argument. And this is this PyCMP is. And so this comparison actually just compares v equals w. And v and w are pointers in C. So this compares the addresses of items. So whenever you are doing x is y, you are actually doing the same thing as if you do ID of x is ID of y. And the reason for that is that in CPython, whenever you are doing ID of an object, it actually returns its address in the process memory. And this address is just the pointer of the Py object. There. So something is the same as, sorry, the is wrong here, it should be equal. Yeah. So coming back, you have similar situation for is not, you just check if those are different. And of course, if this hits, then you break out of the switch, so that we would end up here, and based if the result is true or not, we either return true or false. Yeah. Oh, and by the way, they are using integer for the res variable and not a boolean. The reason for that is that you might have some negative values that will be like errors, which maybe we'll see, or maybe there are none. I don't know yet. Then there is PyCompareIn. So whenever you are doing x in y, like if item is in collection, then a PySequence contain is called, which checks if the result here is negative. And if it's negative, then it returns null. So the reason for that is that you might do x in y, and one of those might be like wrong, and then the rest will have the negative value, which will tell the interpreter, okay, this is some error that needs to be handled by you. Like you need to throw an exception later on. The exception needs to be called by the or raised by the logic that called the CMP outcome. Okay. So then there's the other example, which is not in. That's pretty much the same thing, but with a negation. And then we have the exception match. So whenever you are comparing two exceptions, if one exception is another exception in a except block, this is happening. There is this compare op that's being generated, and this compare op has this exception match argument. And there's plenty a lot of code which we'll not get into because that's a lot, and that's not really that interesting. Yeah, and then you have the default branch, which tells you, okay, if none of those is the correct thing, then we will return PyObject reach compare. Yeah, and then there's this return of Py true or Py false. So coming back to where are we at? We are in compare opcode, and the argument was that the opcode was greater or equal than. On the left side we have x, and on the right side we have 0. So where are we going now? Anyone? Like what's next? Yes, the PyObject reach compare, because none of those cases here match the PyCMP greater or equal, which is the operator here. I mean, our operator that was passed. So we go into PyObject reach compare. And so there's a good comment at the top which says that it performs a reach comparison with object result. And this wraps a do reach compare function, so there's another function that will be called, with a check for null arguments and a recursion check. So this is a wrapper for another function that will be called. And so it starts with this assertion. So the opcode argument here, as I said, there are different definitions for this, and the opcode argument must fit in those values. And this is an assertion. So this code, this assertion, might not be executed in your Python build, because there's an assertion, and assertions are optimized out whenever you are building something. So you probably don't really execute this code. But it's there for debugging purposes. And as the function description told, they check for nulls in V and W, and if that happens, they kind of raise some kind of PyError path internal call if the error didn't occur before, or something like that. And then they have this error enter recursive call and leave recursive call. I'm not 100% sure what's that for because I didn't look into it, but I believe it might be related to like recursion checks. Whenever you are like calling the same function a lot of times, there is like a recursion limit, internal recursion limit in Python. So I believe that it might be this, but I'm not sure. Or maybe the do reach compare can somehow call PyObject reach compare and like bail out in some cases. I don't know. Anyway, the do reach compare function is called finally. So the do reach compare is a bit long because here is a comment that I put here. Just notice that there is more code, so it fits two sides. But for recap, we are in compare op that's called CMP outcome. This called PyObject reach compare, and this called do reach compare. So there are already three like kind of compare functions that are being called, and that's not everything yet. So anyway, there is a comment that calls perform a reach comparison, raising type error when the requested comparison operator is not supported. Because someone might call this, I mean some function in CPython, and it might provide a wrong operator somehow. But anyway, let's look at all of the logic. So first of all, they declare reach CMP func, which is f variable. And this is important because they kind of retrieve a comparison function from Python type objects later on, which we'll see in a second. And then they call it. And they need to do it in such a way, I'll describe it in a second. But basically then we have those three ifs, and then there's another logic which is not there, which we'll see later on, which like switches based on the operator. And here, we have those three ifs, and we might return here based on something. So let's see. The first if condition checks if the V and W are arguments, by the way. If OB type, which is a pointer to a type, if those are different, so if V and W types are different, then we will check another thing, and if all those are true, then we will do something. So the next check here is whether V is a subtype, W is a subtype of V. So that means that W needs to inherit from V in order to execute this part. And then the W type needs to have this reach compare function. We will see what kind of, I mean, we will see this TP underscore thing later on as well, but take it on granted for me that this means that the function pointer needs to be there. So if that's the case, there's some checked reverse operator which is assigned to 1, but then the f, which was assigned here, this reach compare func f, which was assigned here, it's called. Like, the function is called, and w and v are passed, and there is a swapped operator, like mapping, because we swapped the operator left and right sides. And if this result is not pilot implemented, they return this result. And the thing we've not implemented is that there's a special singleton in Python which you can use to return from methods like magic equal or less than or greater than and so on, to indicate that the operation is not implemented with the respect to the other type. So if this comparison doesn't work with this type, just return not implemented from those magic methods. So that the interpreter will try then to compare it in a different order. As I believe, I'm not 100% sure about that. But anyway, so that was the first branch. And there's the documentation of the ref count, which is not really important. They need to track this thing and like decrement it all the time, so it's kind of painful. And then there's this different if statement, which checks for whether the v object actually has this TP reach compare function. If it has it, it just calls it. And does the same logic with like checking for not implemented. And then if the checked reverse op was not set, so we haven't been here, and the W, so the right side of the comparison has this TP reach compare, then it will be called with this swap op operator mapping again. And the result might be returned here. Okay. And as I said, this is not the end of the function, because we might end up with res like PyObject pointer having some value and going further. Like you might have a case where none of those types have reach compare functions. And if this is the case, here this comment means that there was a code before. If this is the case, they provide some kind of sensible defaults for equal and not equal operators, but not for any other. So if you compare two values, then there will be some comparison made, but on the other side there won't be. So they switch based on the operator, and if there's this equal operator, then they just compare the addresses here as before and return true or false. If this is not equal, then they do it the opposite way. And otherwise, they just return type error. That, you know, this kind of comparison is not supported. We bring the instances of those two objects. Because no. Yeah, and that's related to the comment that's there, that when the requested comparison operator is not supported, they throw their type error. Okay, and they increment the results reference count. And for your information, just to come back, where are we? We were in this compare opcode, then in this do reach compare function right now, after some functions. And the question is, which of the path of those codes we'll use here when this do reach compare was called with x, 0, and the operator of greater or equal than. So for sure it won't be this part, or it could be this part, based on the x type. It could be this part, because those two cases are not matching. But it could also be one of those things, because the x might have the TP reach compare, or the 0, the integer, might have the TP reach compare. That wouldn't return not implemented, but even if it would, we would end up here. So the answer is it depends on the x, or actually v, because it's named v in this function, type. So let's make an assumption here, just to not dive too deep. Let's assume that x or v is integer, because that's probably the easiest thing. And we'll also see like how integers are being compared by CPython. So if x, or v actually, is integer, we want to go into this branch because the types of v and w are different. And since they are different, we are not even checking like if whether they are subtype or whether there is the rich compare for w. But we will end up here because the v, which is the x, which is integer, integers have indeed the TP-rich compare function. So then we would call this TP-rich compare function here with x, 0, and this is greater or equal than operator. So let's call it. And regarding this TP-rich compare, here is a part, because that's not the whole picture, of pylon type object. So there's this pylon type structure of a PyType object type, which defines what are the operations of integers, what's the name of integer type, what's its size, whether it has a deallocation function, which is called TP-dealloc, whether it has a special print function, which apparently it does not because it's 0, whether it has getArg or setArg, and so on. And here is, at the end, our TP-rich compare. And basically there's some kind of header at the top that defines some stuff. There's this TP-rich compare, which points to long rich compare function. So there's long rich compare function that will be called. And this long rich compare function looks like this. So obviously it takes some kind of self now, because that's the integer we call the comparison on. It has this PyObject other type and the operator. First of all, it does some check. I didn't really look it up, but I believe it checks what are the operators being called here. Because, for example, you don't really want to call an operator. Since it's called binop, it's probably checking whether the operator is binary, whether it has 2 arguments. Because there are other operators that are just 1 argument. So probably that bails out if it's not a binary operator. And now, if the self equals other, the result is just 0. And the 0 basically means that those 2 integers or objects are equal. And the thing is that they do some kind of fast checking here, so they don't really check whether those 2 integer objects have the same value. They check whether those 2 integer objects have the same addresses. Okay, there's a question, what is the difference between 2 equals 2 and x equals 2 and, x assigned as 2 and x equals 2. If there is any other additional operator excluded, may not. Well, the first one will just use constant values. The second one will need to create a variable called x, assign the value to 2, then make the comparison. So the second solution is a bit slower, and it won't be optimized by CPython because CPython does not do such optimizations. Okay, and then if the addresses are not the same, then we will call long compare function. And here is some kind of return macro to return the result. So let's look at this long compare function. So this long compare finally shows us how 2 integers are being compared in Python. So we have 2 pylon objects, A and B. Now they call it pylon object, not PyObject, because it's better because they need to actually access those fields like OB-digit. So first of all, they have this sign variable, and they are taking a size of A and size of B, and if those sizes are different, then it probably means that those integers are also different, right? I mean, for sure it does, because that's how they implemented it. But basically, if those 2 long objects in Python or integers have the different sizes, they set this sign based on the size, and then they actually want to return a value of -1, or value of 1, or value of 0, so that they will be able to differentiate whether one of those values is bigger or lower, or whether they are equal. That's why there are 3 different values that can be returned here. And it's all based on the sign variable. Okay, so if the sizes of those integers are the same, oh, and one disclaimer. So basically this means that whenever we are comparing 2 integer objects and their sizes are different, the comparison is quite fast, because we don't really execute this whole lot of logic. We just decrement, subtract 2 values and then bail out. But if the sizes are the same, then we are taking the size of A. I'm not sure why there is the ABS, but yeah. And they are checking, they are looking for whether, because there were these OB digit fields, and in a super naive implementation of integer, they could store an array of characters or 8-bit values, where each character would be just the character of the integer. But obviously that would be slow, so they use a different base for those digits, but basically they check whether those digits in those 2 integers are the same. And if they are the same, they are just decrementing the I. But if they are not, then they check whether I was negative, or whether the loop has ended. And then that means that the values are the same, because we iterated over all of the digits of 2 integers. Otherwise, we'll go to else. We'll go to else, and we will calculate the sign based on the digits that differed, and then we'll assign the size in return. So that's how 2 integers are being compared. So, just to remind us, where are we at? Because there were multiple functions that were called, so let's look how many of them. We started with compare operation, which is this opcode. This called CMP outcome function, which then called PyObjectRichCompare, and then this called toRichCompare. Then this called this dpRichCompare of integer. This then called longCompare, which we have seen previously. So it's like 1, 2, 3, 4 functions that are needed to be called. Okay, we don't really measure performance or something based on how many functions were called. But it's still a lot of code that needs to be executed in order to compare 2 integers, where one of them is a variable. This kind of set, I would say. So let's go back to our VM. So we were at the compare operation, and we were as this CMP outcome. So we didn't even execute this, but it will be faster now. Yeah. So we have the comparison result in the result pointer to a PyObject, and this is the result of x equals or greater than or equals 0. And let's assume this result is true. Let's make an assumption here that x was, for example, 10. So then we would decrement those 2 values because they are not needed anymore. Decrement the reference counters. Then we would set the top of the stack to the result. And if we look over the stack manipulation macros, the set top just sets an item that's before the stack pointer to v, which is the argument of this macro. So basically this does change the x there into true, because we assume that the result was true. And the stack pointer stays the same, it doesn't move because it wasn't decremented. Then we check if the result was null. Why is that? Because there was some path in one of those functions that they could have returned null whenever the PySequence something returned an error. And they returned null at that case, and this is this null check. Probably there were also other cases where they could have returned null. And if this is the case, they go to error and handle this error while raising some exception. Then they use those three macros, predicts and dispatch. So I'm not going to cover predict, but this is related to the compute gotos feature of the compilers, which is an optimization technique. Yeah. So it's basically to speed up the code. And then there's this dispatch. So dispatch jumps to the next opcode. And this next opcode here is pop jump if false, with an argument of 12. And this argument here is the address of the instruction where we will jump if the result was false. So we will be at the 6th instruction. Then there's 8, then there's 10, and then there's 12. Because in Python 3.6 and further, the opcodes have 2 bytes. I mean, yes, the opcode and argument have just 2 bytes, each of them. And in some previous versions of Python, those could have variable length, multiple bytes. But here now they have just 2 bytes. So coming back to this pop jump if false, it looks like this. So again, it starts with some predicted macro, which is not interesting. Then they pop out the condition for this check whether we are doing the jump or not. Whether we are going to jump into a particular branch or a different branch. So since they popped, the stack pointer is decremented and the condition is a true value. And we have a question. What is the reason why is integer or long comparison not using some simple comparison that would eventually translate to something like a CMP? Well, I'm not sure what you mentioned by CMP. If you mentioned a kind of easy function from C that does the same check that they did, it's like a simple function. Not using simple comparison. I'm not sure what you mentioned by simple comparison, because so since the integers in Python might have an infinite length, like if I have an integer of, I don't know, 44, I can take it to the power of 4, or maybe again to the power of 4 and get a super big result. And all this works. And this is not like 32-bit integer. It's like this OB-digit array that stores the digits in a given base of this integer, and so they need to handle these comparisons, for any big integer. So previously in Python 2, they had a distinction between integers and longs, and so integers were probably 64-bit integers, and longs were bigger integers. And then the logic of integers was a bit faster, probably. I'm not sure, because they just used a fixed size. But they also had to handle situations whenever the operation result of multiplication resulted in a bigger integer. So they needed to return a long type from multiplication of two integers. So that was a bit fucked up because you had to handle all those cases whenever you wanted to check if something's integer. You also had to handle the situation whether it's a long. And in very, very ancient versions of Python, you could have expressions where some multiplication or some operation would overflow, because the operation of 2 integers didn't handle the check whether it should resize to a long properly. But that was Python 2.4 or something. Anyway, let's come back here. So we are in this pop jumping false. We retrieved or popped out of this the condition. Then we are checking if it's true. If it's true, we just go to fast dispatch. If it's false, so that basically means we go to the next instruction. Because we only jump the pop jump if false. This means that we do the jump operation, jump to a different address, only if the result is false. So if it's true, we will just go to the next operation that's there, the bytecode. So in case it's true, they just do fast dispatch to go to the next instruction. But if it's false, they jump to the op arg, and the op arg is actually this 12 that was there as the argument of the opcode. And then they do fast dispatch. So this jump to macro actually changes the instruction pointer to okay, point to this now. and the fast dispatch just executes this instruction that was being pointed to. Okay, so then we also have this PyObject is true condition. And the question is why? So what the hell does it mean? PyObject is true condition, and before they had cont equals PyTrue. Any idea?
It checks whether the object evaluates to true.
Yes, exactly. It checks whether the object evaluates to true. Because this comparison here just compares the addresses, and PyFalse and PyTrue are singleton objects. So it checks whether this is exactly the PyFalse, exactly false, or exactly true. And in this case, we are checking if the bool of condition is true, basically. And if it's the case, then we also have some like error handling situation here. But if there is no error, we also jump to the operator argument. So this basically means that was false, because we jumped if false. And otherwise, we go to error if there was an error. Okay. So in our case, the cont is PyTrue. So we are just jumping to the next instruction, which is load fast of the x value. And basically, as you have seen, we did this load fast before, but this x value is not on the stack anymore. So even if we would try, we cannot really retrieve it from there. But since the stack pointer is at the top, then in theory we can't. So this loads this x again on the stack. So it just does the push in the end. We won't dive into load fast again because we already did. And then there's the return value instruction. So the return value does basically it. It just pops out the return value. It has some like check, and then it goes to exit returning. Because this ceval or whatever the function is called, like pyeval or something, frame, pyeval, I don't remember, function is called. It's called for a given like code block, like a function. And now we are returning this from this function. Okay, and one disclaimer, because I didn't tell it before. This symbol here means that this is a target of a jump. And this target of a jump is the target of jump if false, like this 12 argument here. So this is like an indicator in this disassembly. Okay, so this basically decrements the stack pointer and pops the value. So now red value is x. Obviously it's here on the stack because it's not here. And then it goes to exit returning, which basically, until the stack is empty, it removes elements from the stack. Because you could have some other elements in the stack from different operations. So we are clearing all this stack, because we are going to a different function or something. So now the question comes, how does it look in code? Like, what does those operations translate to? Like, if you would write it in Python. So the first form of codes is just if x is greater or equal to 0. If this is the case, then we return x. Otherwise, we will load the value of x again. We will make an unary negative operation and return this value. So this unary negative just returns minus x. Okay, my question is, can we write this code differently? So yes, we could in theory. Like, we could use else there, right? Or we could use return x if blah blah blah, else blah blah blah. So let's see what would happen if we would write it using if and then else. So here's this code, here's this of it. So that's the thing we have analyzed. And now let's see a bit different code. And now we do this over it. So let's see it in parts. So first of all, we have the same stuff. Like, we check whether x is greater than or equal to 0. Then we return to this value. Then we also have the same stuff. We return minus x. But there is also this, which is like, after the last return, maybe the last return, we have load const of known and then return value. So my question is, can this function return known? Assuming that x is not known.
No.
No. Well, actually it could, because you could have override the operator of greater than or equal and then return a known. But that would be broken. Or maybe that would raise an exception, I'm not sure. But anyway, the answer is no, it cannot return known. So why the hell is it there?
Every Python function ends with known.
Sorry, louder please.
Every Python function has this implicit return known.
Yes, exactly. Every Python function, if you don't return anything, it has an implicit return of known. So the question is, why it's not there on the left side? Because we always return something. On the right side, the Python compiler doesn't know that. So it generates these actually 4 bytes, or 2 operations, which is kind of an overhead that's redundant, but it happens. It doesn't really analyze whether you have whether if you are branching, whether all the branches actually return something. So that's kind of what the hell, but that's it. That's just how it works. There are many things that are broken everywhere. So let's look at this example. Okay, my question is, are there any questions to the part that was here?
The part that was earlier, there was a pointer to the code object that had 6 bytes. I don't know why, because maybe the 2 zeros were missing, but it's...
Sorry.
The very beginning of when we loaded the code objects. The Marshall loads.
Can we go back into it? Where did I have mouse here? Oh, yeah, I have it. What do you mean 6 bytes?
Oh, yes, this one. Code object module at 0x something like this, and it's 6 bytes there.
You mean this is 6 bytes?
Yeah.
Oh, because that's an address. So addresses have 8 bytes. But you don't really show the zeros at the left side because it doesn't make sense.
Okay.
So that's just a number, just an address of this code object. But it doesn't make sense to prefix it with the redundant zeros because it would take a lot of space if you would print a lot of those.
I suspected that, but maybe there was some obscure reasons like
No. So this address is kind of randomized. You might have a different, kind of based on your Linux kernel version. Let's not talk about it now. Okay, so coming back, any other questions? Yes?
Do you know how negative numbers are stored inside the Python?
How negative numbers are stored inside of Python? So I don't know, but I assume that since we have this OB digits, it's probably stored the same way, and there's this size that can have a negative value, and they did this PyApps.
Yeah.
So this might be a good investigation.
Actually, that's why I asked, because when I saw this apps value,
Yes, it's probably this
size,
size.
it doesn't make any sense unless it's possible to have negative value of pi size. And
Yes, exactly. That's really a good point. Thank you. Okay, assuming x is a number isn't just an implementation of apps. Well, it is. It is. Yeah. So let's see another this example, just to get a bit more into disassembling Python. So if we have the function like def foo that prints something, it does the power of x to 2, returns that y, and there's a return. This looks like this. So first of all, oh, and by the way, this is good. I mean, the this function actually makes a new line here and here, just to notify you that probably those 4 belongs to like one line of code, and those 4 to another line of code. And this line of code number is written here, 642, which I stripped from here, sorry. But yeah, that was the whole file, so yeah. So we do load global of print. Because print is just a global, you can change it. You can like override print with another print function. And then we load the const of the string. Then we call the function, and basically this call function has this arguments of 1. And this means that there is just one argument that's being passed into this function. So the argument of this opcode call function is just number of function arguments. And we also have this pop top to like remove the result from the function. Yeah, because we don't really use the result of print function. Print function probably returns no, I'm not quite sure, but probably yes. And we just remove this result from the stack. Then we do this line, and in here we just load the x value by load fast. Then we load the constant, like those 2 arguments for the binary power instruction or opcode. And then we do store fast to store it into y. So just a disclaimer, whenever you see load fast or store fast, it means that you are referencing the local variables. If you would reference globals, you would see load global or store global. If you would reference constants, you would see load const or store const. I'm not sure if you can store const, by the way, probably not. And I think there is also load name and store name, but that's probably for like referencing attributes of something. Yeah, I'm not quite sure, but probably. And there is this return y that just loads this value of y and then returns it. So that's kind of weird because those 3 here could be optimized out. We could just return the value here because this return of binary power was already on the stack. So we could have returned it here. But again, there is no such optimization. That's the code that needs to be executed. You stupidly assign this y variable and then return it because you have written it like that. And so, yeah. I might have another example, hopefully, with decompiling Python code, because as you have seen, we just did some disassembling of it, but there are also decompilers. So there are programs that changes the bytecode into Python source code. They don't necessarily always work fine, because there are cases in which it's super hard to like retrieve some data out of it, but it's for most cases it's trivial, but there are cases where it's hard and they don't really support them yet fully. And they don't really support all of the Python versions. I hope I have this tool here, yeah. Okay, so I do uncompile on this PYC file, I will get the source code back. So when might it be helpful? It might be helpful for you if you would have such a situation that you would lost your source files for some module that was imported. Like for example, you had it open in some IDE and then your computer shut off suddenly. Then you open your computer and see that the file is empty because the file was being written by the IDE and then, oh crap, it's not there. So then you can look over the PYC files and you can decompile them and get the source code back. Or you can always like do this just for some research, I don't know. Okay, and that's all from me in this talk. I hope you enjoyed it. If you have any feedback, please tell it to me later or send an email or whatever. If you have any more questions, either raise your hand or slido.com. If I have to say some summary, it's probably hard to sum it up, but the thing is that in CPython there are tons of operations that are being done. And you have seen that, for example, for a simple case comparing two values, there's so much code that's being executed. And that's both a bad side of Python, but also a powerful side of Python, because there's a lot of work that was put into it. And you can always contribute if you want. Thank you. So any questions? Any easy questions? Yes?
Do you know if it's possible to make a stack overflow exception in Python? Because this push instruction adds new value to the stack, right?
It does, as far as I know.
Okay.
So the question was whether it's possible to trigger stack overflow of this internal stack. What was your answer, sorry?
I think it's not possible because there's an explicit check for the stack size in the C code.
So honestly, I don't know. Probably there is some. Yes?
There was a comment on the C code saying that the maximum stack size was max int. So
Yeah, it was even visible on the presentation.
Okay, so
just reach max int.
so the maximum stack size is max int, which basically means
2 million.
that your Python program will end up crashing because it will probably fill out the maximum stack memory of your program and it will segfault on Linux at some point. But an interesting thing here, you might have to show something else. Maybe I won't show this in the code, but the thing is that if you would write try in a try, in a try, in a try, in a try, like 20 or 30 times, with some exceptions, and run this code, you will get some error, some fancy error like XXX block stack underflow or something like this. And this is mainly because they do check how deep you are in some things called iBlocks, and the maximum iBlock is 20. And you can recompile CPython changing this value. And because that's set in a macro. But yeah, that's like a weird check that's there. Yes?
I believe I reached stack overflow once because I changed the recursion depth. So I maximized the recursion depth. I was just experimenting just to see how far it would go. So instead of getting the error regarding the recursion depth, I just reached stack overflow because it was recursive like 1,000 times and it just blew up, so that's a way to do it.
Yeah, because basically the recursion is based on the stack.
Yeah, so it's keep adding stuff to
You
the
still
stack.
have the protection from the stack limits inside the functions, but there was no limit in case of the recursion.
Yeah,
Yeah, it makes sense.
So the stack blows up before recursion blows up.
So it's still possible.
Yes.
If you really want it.
Okay, sorry, I didn't track the discussion, but you said that you changed the recursion limit of the interpreter and you hit the stack overflow.
Yes.
I mean, segfault, right? Did the code segfault, or was there an explicit exception for Python?
It's a Python exception.
Okay, so maybe they handle some of those situations.
I get segfault when I mess with C types.
Oh yeah, that's the case, definitely. So the thing I was talking about is this fatal Python error, XXX block stack overflow. Whenever you run a script that does something like this. And the story of this is that I have played some CTF challenge where you actually got some crazy, stupid file that looked like this. So you got a result of this.this, which is super long because it has 10,000 lines of code or something. But there are patterns here. So they actually load name of some custom exception and they compare operation. So this is basically handling the except case, if I recall correctly. And there's setup finally as well. So there's try, blah blah blah, raise some exception, except, and then finally. And this is done multiple times, deep as hell. And so I basically wrote a parser for this, which was an overkill solution, but yeah, but this code looked more or less like this, and many times more of these try catches. And if we want to see this limited CPython code, where is it? It's CO max static block nesting within a function, and if we search for it, Probably not necessarily in this file. Wow, I don't see the search bar. Hopefully GitHub will search for it because GitHub search is not good. Oh, it's here. In Python compile C. Oh, so there's even more of those checks, which is like high exception, syntax error, too many statically nested blocks. Or maybe that's how they changed it in some version. Because I was expecting to see this fatal blah 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 error. So that's basically it. There's nothing more. Thank you very much.